Hi, I'm Cameron Riddell, and I am a known practitioner of frequentist statistics. In my journey to become a more well-rounded data scientist, I have explored some of what the Bayesian perspective has to offer, and I must admit, I liked what I saw. Today, we'll discuss the following topics. We'll compare frequentist and Bayesian statistical philosophies. We'll understand how to model a simple game with Bayesian statistics. Then we'll go ahead and demonstrate how to perform a grid search to calculate parameter likelihood estimation. And finally, we'll wrap up with a brief demo in PyMC4. We have so much to cover today, but first, I'm in the Bayesian corner, and you're in the frequentist corner. We're mortal enemies, right? Well, contrary to popular belief, these two statistical perspectives aren't quite as different as you might think. And I don't think that their camps are fighting anymore, but they do have some differences and they make different predictions because they end up asking different questions. So instead, we have to come to terms that both of these approaches operate differently and agree on many of the problems that we encounter. But where these approaches might differ, well, that's not due to one approach, frequentist being correct or incorrect, and Bayesian being obviously the opposite. It's simply a case that they are interested in answering different questions. And we have to keep in mind the historical perspective of where these two theories came from and how they have been adopted into modern day use. So today we're not here to prove that frequentism is better than Bayesian stats or vice versa, but simply to compare how each approach works with the probabilities in the world around us, and that they both focus on an attempt to capture the regularities that we can use to create reliable models and estimates of the things that we interact with every day. Many natural processes can be modeled in statistics. It just takes a little bit of thinking to figure out how we can do that. In this first portion of today's seminar, I want to discuss what is frequentist statistics and why do I care? Instead of giving you some Wikipedia or dictionary definition of frequentism, I want to describe to you what frequentism is and how it works. And so in frequentism, we are always considering null hypothesis testing. And so you'll commonly see frequentist statistics start out a little bit like this. Under the given hypothesis, how unusual is the observed result? Whether that observed result is the mean of a sample, is the comparison of two means from two samples, or maybe the comparison of means from many samples, or we can do something like a chi-square test and we can say, did the number of times I observed this event exceed the number of times I expected to observe this event? And so there are many, many different questions that we can ask with frequentist statistics. And we should note that frequentist statistics gained a lot of popularity and a lot of use back in the early manufacturing days, where we would do things like bottle beer or bottle water, and we wanted to test, okay, if I take 10 bottles that I just manufactured and I test all of them, what's the likelihood that the larger population of bottles might be contaminated based on the data that I observe in my sample? And so with frequentism, we are always concerned with, if the null hypothesis is true, what is the probability of the data that we have observed? We'll be coming back to this probability notation quite a bit. Frequentists often observe that probability is a limit of the relative frequency of an event after many trials. This is why we perform sampling statistics whenever we talk about frequentism. I think one of the best points that highlights what frequentism is and why we use it, or why we might use it, is a simple test of the sample mean and related back to our abstract population that we might not have access to. Going back to my bottle example, if I can't open every bottle I manufacture, which makes sense because how would I sell them? Well, how would I make any logical assumption as to whether or not, if I see one bottle in my sample is contaminated, how many bottles should I expect in my population to be contaminated? Well, something that we can do is we can perform sampling statistics. In sampling statistics, we assume that there exists some abstract population that we cannot measure in its entirety. And we take a sample from that population. A lot of sampling statistics theories in sampling statistics can be proven by simulation, so we'll do just that. What we're going to do is we have this theoretical population whose mean is 100 and has a standard deviation of 5. We'll go ahead and sample 10 values from that population, and then I'll plot those 10 values on this here chart. So let's go ahead and run this code. You can see that in my sample from my population with mean of 100, I observe values as low as just under 94 and as high as just under 107. And based on these 10 samples, I might be so inclined to take the mean, which is this orange vertical bar, and I might come to a conclusion that the mean of my population based on my sample is just over 100. And as it turns out, right, since we know the population in this exercise, well, it turns out that a mean of 100, of about 100 in my sample is actually quite good. Well, if we repeat this simulation process and we don't just sample 10 individuals or 10 times just once, what if we repeat that simulation 5 times? And so here on the y-axis, you can see each of my simulations, and my blue circles represent my individual observations, and my orange vertical lines represent the mean of each of those observations. And what I want to direct your attention to is that these points, these individual values, actually can vary quite greatly, especially when I'm drawing sample size 10 or maybe even larger things. We'd expect to see even larger variation. But what doesn't vary as much are these sample means. These orange means tend to hover around the same value. And in fact, they tend to hover around 100, which is the population mean. We can see here in my 5th sample that I drew, we got a very odd mean. I see a lot of kind of outlier points relative to my population here. But let's go ahead and let's repeat this. Instead of just 5 times, let's repeat this 50 times. And what you can really see here is that my orange lines, which denote my sample averages, really hover around that population mean of 100. It turns out that if I repeat the simulation, and we'll repeat it 100 times, and what we'll go ahead and do is we're going to create a histogram of all of those means. And in our histogram, all we're going to do is observe how often each of those sample means appears. So what you can see here is that in my histogram of the observed sample means, right, my 100 sample means, this is what's referred to as my sampling distribution of the mean. And in my sampling distribution of the mean of size, right, sample size 10, I can calculate what's the probability of observing a sample mean given that it came from a sample of size 10. And so I've simulated this sampling distribution of the mean. And so if I go ahead and I have a new value, I have a mean whose value, I have a sample whose mean I know, but say I didn't know for a fact that it came from this original population. In fact, my sample mean that I just observed has a mean of 100 or 101. Well, it turns out the mean of all of my sample means, or my simulated means, right, lies exactly on the population mean, which is a good thing. Then I have this observed mean over here on the right. I can use the area under these histogram bars, right? Right now we have counts. I could normalize this into a probability, and I can use the area under each of these bars to figure out what is the probability of observing a sample whose mean is 101. And since this green vertical line lies quite close to the center of my distribution, I might think, okay, well, if I took a sample, if my null hypothesis is true, right, if the population has a mean of 100 and I get a sample whose mean is 101, well, that doesn't seem to, conflict too greatly with my null hypothesis. I think our probability of observing this sample mean is quite within the realm of possibility. And so we might come to fail to reject our null hypothesis and move on with our life. But this leaves us with a slightly dissatisfying answer. And that's because, well, if I change my sample mean to, instead of the 101, instead, I will place my sample mean at 103. And let me go ahead and turn off this other figure. And now if my sample mean is at 103, well, it seems much less likely that a population whose mean is 100 could have generated this sample because the mean is way out in the tail. Although it happens, I now need to come to a distinction. I have a decision to make. Did this sample mean originate from a population whose mean was 100 with a standard deviation of 5, or did it not? And the fact of the matter is there's no yes or no solution to this question. I need to create a cutoff. This is what we refer to commonly as our alpha criterion in frequentist statistics. I need to designate some proportion of probability or some amount of probability where any sample mean that exceeds that probability, well, I'm going to reject my null hypothesis. And this cutoff point, this alpha criterion, is more or less arbitrary. Commonly we use 0.05 as our alpha level, our p-value cutoff to designate a statistically significant finding. But then at the end of the day, all we can say is, well, I rejected the null hypothesis, or no, I did not reject the null hypothesis. And for some questions, this is enough. All we want to know is if I gave a study session to a group of individuals and I gave them pre-test before the study session, I gave them a post-test after the study session, did they improve? The null hypothesis there is no, they did not improve. And if I can reject that, well, great. I've produced some statistical reasoning that these two groups differ. But how do we apply this idea in the absence of population sampling? Right there, I just showed you a simulation. And so if I have a sample with, say, these values, I can go ahead and I can actually calculate or estimate various parameters about my population given my null hypothesis. And I can do things like calculate or estimate the standard deviation of that sampling distribution of the mean. And I can even go ahead and model that and then stack up my comparison. And this is essentially performing a z-test for me. So we'll go ahead and just take a look at these results. And you can see that for this given sample that I just provided, the probability of observing the sample mean or greater is extremely low. And so in this case, I would reject my null hypothesis. And this is what frequentism is all about. It lets us know the probability of observing our data given some static hypothesis, I'm saying my population mean is 100. Now it's up to me to either reject that null hypothesis through testing or fail to reject it. But what about Bayesian statistics? Well, with Bayesian statistics, we flip kind of the philosophy, the interpretation of probability on its head. What we say is that given an observed result or given some data, what's the probability that the hypothesis is true? And this is in stark contrast to what we just discussed for frequentism, because frequentism said that given the null hypothesis is true, what's the probability of observing the data? And Bayesian say, given the data, what's the probability that the hypothesis, not necessarily the null hypothesis, is true? And this lets me test not just one, but an infinite number of hypotheses, evaluate how likely those hypotheses are to have generated the data I'm observing. And then from that, that's what we call a posterior distribution. From there, I can describe my data in any way that I like. So frequentists interpret probability to be related to frequencies of observed events, whereas Bayesians say that probability is related to the certainty or uncertainty of events happening, like the certainty or uncertainty of rejecting or failing to reject my null hypothesis. And so we commonly refer to these as a variation in belief about parameters. So we're saying, okay, the population mean could be 100, but it could be 101, it could be 100 or 99. The thing is that all of those populations could give rise to the samples that I am observing. And so let's go in this is the most math I really want to talk about, but what is Bayes' theorem? Well, Bayes' theorem posits this. It posits that the most interesting thing to examine here is the posterior probability. And this is the probability of my hypotheses, plural, given my data. And we can estimate this value by multiplying our likelihood, which is the probability of observing our data, given a single hypothesis, times our prior, so our beliefs about our data, or our beliefs about each hypothesis in the absence of data. And then we normalize over the probability of our data. This is typically a normalization constant, and we don't want to get into too much depth about this. So focus mostly on the numerator and the left-hand side of this equation here. So let's go ahead and talk about Bayesian inference. Bayes himself actually proposed a billiard game. And in this billiard game, we have two players, Alice and Bob, and they absolutely love to place wagers. And so in this game, Alice and Bob have a billiards board or a pool table, and they divide it into maybe uneven sections or maybe even sections. But you can see here that Alice owns most of the board. What we then do is we roll a ball on that board and we watch where it lands. Whoever's portion of the board it lands on, we say is the winner of that round. And so in this case, Alice has clearly won. But like most of the things in the world around us, we cannot directly observe the causal events that give rise to phenomena. So instead of clearly labeling Alice and Bob's, we have this black box here. We roll a ball, and all of a sudden, out of this black box, we hear a whisper, Alice, meaning that Alice won this round. And so how do we go about estimating what the proportions of this board that Alice and Bob own in order to give rise to the observed events, aka Alice winning this round and maybe even more events? Well, frequentists would say that, well, we would just roll this ball 1,000 times, and then we would just calculate the proportion of number of wins that Alice has and compare that to the proportion of number of wins that Bob has, and that's a good estimate for the proportions of the board that they own. But Bayesians want to say, I get that there's a likely estimate, right, based off the proportions, but I want to know the uncertainty around those estimates too. And so if we play this game and we just play 3 rounds, Alice wins once, Bob wins once, and then Alice wins again, well, we have a total score of Alice with 2 and Bob with 1. And we want to ask ourselves, what are the possible divisions of the billiard table? So what we can do is we can actually model each of these scenarios. We can model each of these hypotheses. If we can say, okay, if we divide the board into quadrants, our first hypothesis is that Alice owns absolutely none of the board, and Bob owns the entire thing. In our next scenario, Alice owns 1/4 of the board and Bob owns the other 3/4. They each own half the board, and so on and so forth through all of our scenarios. And you can see we have 4 or 5 scenarios laid out here. So we're curious about the question, what's the probability that any of the above scenario generated our observed events? And remember, our observed event is just Alice, then Bob, then Alice. And we can reason about this very logically. If I have these scenarios and I note that I see Alice, then Bob, then Alice, I know for a fact this scenario, incredibly implausible. This is never going to be the truth of the world because in this scenario, Alice doesn't own any of the board. Therefore, Alice could have never won a single round. So just by logic, this scenario is kind of out. Well, it turns out that these hypotheses here in the middle, well, they could have all given rise to the data that we observed. They could have all generated a sequence of Alice, then Bob, then Alice. But what we're curious about is how likely did each of these scenarios actually give rise? So what we'll do here is we'll actually expand our data just a little bit. Up here, you see our sequence, which is Alice, Bob, then Alice, and we see the number of ways that we could have arrived at this sequence. Of course, the first time we see Alice in our first scenario, remember Alice doesn't own any of the boards, so this is impossible. In our next showcase, we have Alice, okay, this is a 1 in 4 chance that we could have seen Alice. Then on our next sample, well, Bob has a 3 in 4 chance of winning, and in our next sample, Alice has another 1 in 4 chance of winning. If we combine all of these variables here, we actually start seeing a slight pattern. And so I'll go ahead and show this version of our data frame. We can actually calculate how many different paths we could have gotten to produce our observed results of Alice, Bob, and Alice. And all we do is we just multiply all of these values together. This gives us the number of unique paths to get to this result. Well, when we do that, you can actually see that in our second, in scenario number 2, right, where Alice and Bob each own half of the board, well, it turns out there's 8 ways to produce this same result. And in our third scenario, there's 9 ways to produce that result. We can actually repeat this as we encounter more and more data, and we can see that this third scenario really starts pulling away. And so these raw values are just the number of ways that these results, these data could have been observed. We can transform these into probabilities, and we can start saying, hypothesis number 3 or scenario number 3, it's looking quite good. And so it turns out that there's a generic formula for this 2-player version of this game. So if we set up our same scenarios and we ask, what's the probability that any above scenario generated this much longer observed scenario? Well, we'll go ahead and look at our scenarios here. They're the same as they were before. Now we'll look at our value counts. How many Alices and how many Bobs did our sequence produce? What we can do is we can actually take our scenarios and take that same product that you saw before, and we can estimate the same value just by taking our scenarios, right, the number of wins and losses, and then multiplying or raising that to a power of how many observations do we have of those wins and losses. And so we actually get those same values back out, and I'll show you that these are the exact same, right? We have our number of paths of 27, 5, 12, and 729, and this is just kind of a shorthand formula that we can use for this binary outcome. In fact, this is the same formulation that our beta distribution will be using. And we'll discuss that in just a moment. But now if I instead represent our scenarios, instead of by 0 and 4, 1 and 3, 2 and 2, I'll just represent our scenarios as the ways that Alice could have won. And so to do that, we'll go ahead. And here we have our possible proportion. This is our proportion. I'll relabel this because I think it's going to be much clearer. Proportion of table that Alice owns, right? So here we have all of our scenarios, right? And instead of using two numbers, we're just using a single number to represent it. And then we have our ways to produce our observed sequence. Well, we can simply calculate the probability of those observed sequence by dividing it by the total number of paths that we could have taken. And this will be, right, the sum of all of our ways to produce. And so this is kind of our normalizing constant, but you can see here that we now have a strict probability associated, or a likelihood, I should say, associated with the accuracy of this scenario. And we can see that if we were to take all of this data and plot it, well, I need to relabel this. But if we do this, we'll see our very first glimpse of what the posterior probability is. So I'll go ahead and fix that. And we'll go ahead and generate this plot. This is our posterior distribution. And what is the posterior distribution? Well, it's the likelihood of each of these hypotheses, right, on my x-axis, creating the data that I observed. And so you can see that the 75%, the scenario where Alice owns 3/4 of the board, is my most likely hypothesis at being true. And so this might be the hypothesis or the scenario that I want to go with when I'm creating a model. Bayesian statistics is all about creating generative models, so models that produce data for us, and then linking the data that we observe back to that generative model to try and say what the probability is that we observe these data. And so let's go ahead and talk a little bit more about how we can estimate this posterior. Well, we can do the exact same thing that we've seen before and divide by the sum of all of our possible different paths we could take to draw the sample that we did observe. But what I think would be even better is if instead of 4 scenarios like this in this posterior that we have here, and let me rename this, instead of just 4 scenarios, what if we had many? What if we had, say, 10 scenarios or 5 scenarios? And so here are the 4 scenarios that we saw earlier, or the 5 scenarios, I should say, right? 0, and then we have 0.25, we have 0.5, 0.75, and 1. Well, what if instead we had more? Let's go ahead and make 10 scenarios now. You can start to see this distribution taking a little bit of a shape. Instead of 10 scenarios, what if I test 30 scenarios? Well, with 30 scenarios, you can really see a shape on these bars, and they really start to peak somewhere between 0.6 and 0.8. And this is the whole point of Bayesian statistics. I'm not saying that there exists a single parameter that says Alice owns exactly 73% of the board, and that's how we saw our data. In Bayesian statistics, all we're saying is, well, that's the most likely theory, the most likely scenario, but there also exist alternatives in which this data could have existed as well. Alice could have owned, right, 71% of the board, or Alice could have owned 75% of the board. And so that's what the posterior gives us. It gives us the likelihood of each of our scenarios or each of our possibilities. I want to walk you through a brief demonstration on how we calculate this. As you saw, I used that prod function in order to calculate all of the probabilities of each theory or each hypothesis. And what I want to show you is that when we start with Bayesian statistics, we need something that we call the prior. And this is the probability of any parameter in your hypothesis. And so in this case, I'm starting with what's called a flat prior or uninformative prior. I'm making no assumptions that Alice owns more or less of the board. In fact, I'm saying that Alice and Bob probably own the exact same board. This is sounding very similar to a null hypothesis, but it's quite different. And so for this prior, I'm saying there's no preference for the proportion of the board that Alice owns. And so all I'm going to do is rely on the data that I observed in order to develop that posterior. And so let's go ahead and look at that posterior. Just look at one tick of our data. And remember that our data, the observations that we made, started with Bob and then went to Alice, and then we saw Bob 2 more times, and so on and so forth. So let's go ahead and take a look at this posterior estimate now. All we've done is taken our very first observation. We saw Bob come up once. And what we can conclude from this is that the most likely result, the most likely scenario or world where Bob will win just one time and nothing else happens, well, is a world in which Alice owns none of the board and Bob owns all of the board. That's the most likely scenario. But what I'm not doing is I'm not rejecting any other scenario. I'm just saying, well, they just become less likely. And in the case that Alice owns the entire board, well, that scenario is probably impossible because clearly Bob won. Let's go ahead and start adding more and more data into our plot. So instead of just the first part of our sample, let's look at the first 4 parts of our sample here. And so we'll see this plot update. We can see Alice, then Bob, and then we have another Bob. And you start to see this distribution take shape, and there's a preference right now. Bob has won 3 times, Alice has won once, so it makes sense that there's a preference that Alice owns less than half of the board. And as we include all of our data here, well, we see this distribution slowly start to change and take shape as we keep adding values from our sample. So here we've added more Bobs. Here we've added another Alice, and you can see the more Alices we add, the more this distribution starts to shift to the right, indicating that the most likely estimate of our population is above 50%, exists maybe somewhere between 0.6 and 0.8, which is the same conclusion we came to before when we were just doing the simpler scenario analysis. But what about models with more than one unknown? Right there, we're just modeling, just tell me what Alice knows or tell me how many times Alice has won. What if we want to do something like a linear regression? Well, in here, we actually need to model many parameters. I've just drawn a simple ordinary least squares of frequentist statistical approach, which does a very good job at putting a line onto our data. And it seems, or it is the case that for simple problems like this, Bayesian and frequentist statistics tend not to disagree. But what I'm not doing here is I'm not explicitly modeling what are all the possible slopes, what are all the possible intercepts, and what is the amount of reasonable error in my predictions that I can allow. So Bayesian statistics would tell us to model this problem. And so what we'll do here is we'll actually generate the same data set, and we're going to use PyMC4 in order to derive estimates of what is the likelihood of all possible slopes, what's the likelihood of my possible intercepts, and what's the likelihood of my possible errors. So you can see that I'm able to actually model these with underlying distributions. I can say that the intercept is a random normal intercept. The slopes also are derived from a normal distribution, and the errors are derived from a half normal, right? Because this is a sigma, it has to be greater than 0. We can use mathematical operations to define what we're using for the expectation of our outcome. Here, we're interested in the average prediction performance. And then we finally wrap up with what's the likelihood of observing the things that we observed. Well, this is extremely hard to do with a grid search. In a grid search, all it would do is actually calculate all of these different parameters and expand them into a multidimensional space. And with 3 parameters, I could do that. But when we get to any reasonable model that has 4, 5, 6, or even hundreds of parameters, it's going to be impossible because we're going to just run out of memory. Instead, we can use a much smarter algorithm, such as provided by PyMC4, which intelligently samples our posterior distribution in order to draw likelihoods about each of our observed hypotheses or scenarios. And here, I've plotted the marginal distributions, and all marginal posteriors are is just saying, out of all of my hypotheses for my intercept, this was the most likely, where my intercept was 1. Out of all my possible values for my slope, this was my most likely one, where my slope was about 2.5. And finally, out of all my possible hypotheses or scenarios for my error, well, we seem to get a value of hovering around 4.5. And the great thing is that the real values of my slope, intercept, and error were 2.5, which was dead on for my slope, 1 for my intercept, which was very accurate, and then for our error, we got a 4.5, or at least the most likely value of 4.5, but that's the great thing about Bayesian statistics, is we're not talking in absolute truths, we're talking about probabilities and likelihood. So in review, Bayesian statistics is kind of the opposite, the flip side of frequentist statistics, and Bayesian acknowledged that population parameters can have many plausible values, and the whole point is finding the plausibility of those values. For most problems, you're going to have a lot of success with frequentism. For just small and quick problems, the computations are already solved and found, and so there's no really advanced modeling techniques that you'll need. And for Bayesian, you'll find that this is great for having simple interpretations for complex problems. But I see that that takes us to the end of our session today. Statistics is a massive part of data science and the analytic work that we do every day. And whether you currently use Bayesian statistics or frequentist statistics in your work, that doesn't matter. What matters is that you're able to understand the approach that you are using so that you can adjust and interpret your models of the world around us to accurately predict its events.